There was one more slide I meant to add in that last video. So when we talk about satellite data, we can actually, okay, so we can use different wavelengths to see weather, different wavelengths of radiant energy. Cloud cover that we look at so this is talking about satellite data. When we look at that visible channel of the satellite data that I said is like looking at it with your eyes or taking a picture with a camera, we are actually seeing the visible spectrum that we normally see every day. That's why it's just like that. At night, it goes dark. You can't see it when the sun's not shining on that part of the world. Now, we also look at the infrared channel, and what that is doing is that is taking the uh, wavelengths that the Earth is emitting in the infrared spectrum, so about 10 microns, 9 to 10 microns, and it is converting that to a temperature. It's using some of the equations that we saw, and it's actually converting it back out to a temperature, and then it's plotting it on that map. So we can see the temperatures of the cloud tops. The reason why this is really useful, not only have we seen that you can see a lot of different details and you can get a lot of information about temperature, which can tell you how thick and how high up in the atmosphere clouds are, but also you can use infrared imagery at night because the Earth is always emitting, where the always emitting long wave radiation. It is only has shortwave radiation being emitted or being reflected during the day. That's it. So here's a link to the satellite data if you want to go poke around with that and look at those different channels and see that you're actually looking at radiant energy and not just images. Okay, so next up we're going to talk about what happens with radiant energy. So when an object emits radiant energy, it loses it. When it loses energy, it's emitting it, it will cool. And when an object absorbs radiation, it gains energy and it will warm. Okay? If something emits and absorbs at an equal rate, that means that the temperature will stay constant, and this is said to be a black body. So that means that whatever energy is hitting it, it will absorb, and then it will convert that and re-emit it out, so the temperature stays the same. The definition of a black body is an object that absorbs all the radiation that strikes it and emits the maximum amount of radiation that's possible at the given temperature. So back to one of our equations that we saw in the last video. So some rules about a black body is it actually is not the color black. I don't know why they chose to name it a black body, but it doesn't have to be black. The Earth and Sun are both black bodies, and it's proven by those two other laws. We don't do that. We don't dig that deep, but that's why we can use those two laws because it is a black body. At any one given time, the Earth is half in daylight and half in darkness. So the sun, all of the energy that it receives, it emits back out at that really high temperature. The Earth, all the energy it receives from the sun and actually from the atmosphere, it will emit back out, but at a much lower temperature. And we know that by the wavelengths. Okay, so the point where the incoming energy from the sun equals the rate of outgoing energy from the Earth is called the radiative equilibrium temperature. That means that we can determine the temperature that an object should be by knowing how much energy is coming in and how much energy it is emitting. For the Earth, that temperature should be 0 degrees Fahrenheit. Okay? People have done those calculations. We don't have to. But what we've learned, right, is the Earth's average temperature is actually 59 degrees Fahrenheit. So what's going on? Like, why is that the case? So now we get to talk about something called selective absorbers. The Earth is a black body and there are things happening in the atmosphere that help create a climate that sustains life at 59 degrees Fahrenheit. Because if we were at 0 degrees Fahrenheit, there wouldn't be plants for us to eat. Animals wouldn't survive. We wouldn't survive. It'd be really bad. So, much like the surface of our planet, the atmosphere also absorbs and emits radiation, but only at certain wavelengths. the atmosphere is not a black body. So remember, the black body, whatever radiation comes at it, doesn't matter at the wavelength, it will absorb it and emit back out. And then it has an equilibrium temperature. But the atmosphere isn't like that. There's certain wavelengths of energy that come to the atmosphere, and the atmosphere doesn't have anything to do with it. But there are other wavelengths where the atmosphere does absorb and emit those. And these are called selective absorbers. That's an object that only absorbs radiation at certain wavelengths. The way to think about this is kind of like your car's windshield. It is a selective absorber. It absorbs some infrared radiation and ultraviolet radiation, but it allows visible light to pass through. So, like when you're sitting in your car, if you put your arm out of the car where it's not behind a window, but the rest of your body is like beneath the windshield and the sun is beating down on both of you, you will not get sunburnt, at least not very badly on your body, but your arm that's just out there to absorb the ultraviolet radiation will get sunburnt. So the windshield is absorbing the ultraviolet radiation, but it is not, it's letting the visible wavelengths through. So another physics law, this just says that it's Kirchhoff's law, a good absorber are good emitters at that particular wavelength. So if you have something that absorbs really well in the long wave radiation, it will also emit back out, because remember, anything with the temperature emits. So let's look at another plot. Here we go. We have this plot, which can be very complicated. It's in your book. Please read about it if my explanation does not help you enough. Again, on the bottom, we have wavelength in microns, and then we have panels. This is for the whole atmosphere, okay? This is just for carbon dioxide. We're looking at the wavelengths that certain parts of the atmosphere absorb and emit at. This is water vapor, oxygen and ozone, methane, and nitrous oxide. We're really just going to focus on water vapor and carbon dioxide. But these are just panels of the same plot that are showing what wavelengths these different things absorb and emit at, and so where they're selective absorbers. So this shows the whole atmosphere together. We'll get into that in a minute. Here we have water vapor, and how you read this. So they've done a nice job of putting that little rainbow in there so we can see where visible light is, right? And that's 0.4 to 0.7. So for water vapor, wherever we have these peaks, that says that this gas is absorbing that wavelength and then emitting at that wavelength. So there's no peaks in the visible spectrum. So that high energy radiation that's coming from the sun and in the ultraviolet, the UV wavelengths is coming right through. It's just coming right through all that water vapor. But water vapor starts absorbing at about 1 micron. And then we have a bunch of these peaks, right? 5 microns, or actually it's like 7 microns, it absorbs a lot. And then greater than 10, it absorbs a lot more. Do you remember what wavelength the Earth emits at? Its peak wavelength? It's about 10, 9 or 10. Okay, so let's look at carbon dioxide. Again, we have visible light is not absorbed, UV radiation not absorbed. But then we have a couple peaks here where we have longer wavelengths. Again, when it gets to be greater than 10, big absorption and emittance. Emittance means that water vapor and carbon dioxide are absorbing that energy and then re-emitting it at that same long wavelength. And finally, we have the whole atmosphere. Okay, we can see that here UV radiation is absorbed. Where is it absorbed? It's absorbed because of ozone. Then we have a tiny bit of absorption and emission in the visible spectrum. And then when we get to the long waves, the atmosphere is just absorbing and re-emitting it, because each gas does a different selective absorbing of these wavelengths. But if you look at all of them together, this is what it looks like. So the atmosphere doesn't really absorb visible light, which is what most of the sun radiates at, right? And then UV light does get absorbed. So into the surface, what gets to the surface through the atmosphere is this visible spectrum. But then as the Earth is radiating at these wavelengths longer than 10 microns, the atmosphere is catching that and re-emitting it back. It's re-emitting it down, it's re-emitting it up, all over. Okay, so now you have an in-class lab activity. You will be answering some questions about this lovely graph, so please get familiar with it. And those selective absorbers are like our deeper level of how the greenhouse gas works, or greenhouse effect works. So, variable gases absorb most of the radiation from both Earth and the sun, but mostly from the Earth. So they also emit radiation in those same wavelengths, directing that heat energy back towards the ground, where the Earth surface will absorb it again, and out to space. So the atmosphere is like a blanket. It's insulating the Earth's surface, and it is the reason why our temperature is not 0 degrees Fahrenheit, which it should be if we didn't have an atmosphere, but 59 degrees Fahrenheit, where we can all thrive. Okay? It's called the greenhouse effect, and it's made possible by those selective absorbers. So please take a minute to watch this video. So, enhancing the greenhouse effect, right? In chapter 1, we talked about CO2 levels and how they're rising. Well, you could see from this plot that to keep the temperature of the Earth at a livable level, we need carbon dioxide to do its thing. It's a very small amount, but we need it to do that. We do. The thing is as CO2 is increasing, then that means that the effect of that selective absorber is increasing. So we don't want CO2 to not do its job at all. We don't want to get rid of CO2. We just want it to stay at the same level so our temperature doesn't increase. The more CO2 that's in the atmosphere, the concentration, the more of a greenhouse effect it has, which is what's causing our temperature to rise. There's a net warming. Okay. Here's another class exercise. Without selective absorbers, the greenhouse effect, the Earth's surface would be much colder than it currently is. Is that true or false? Okay, so now we're going to switch gears again, and we're going to talk about a couple other things. So that's the main thing that happens with the sun's radiant energy. It comes into the atmosphere, and then it's absorbed by the Earth's surface, and then the Earth's surface radiates back out at long wave. The atmosphere selectively absorbs just those long waves and radiates it back down and up out of space. There are a couple of things that happen with energy that we have to talk about. We have to talk about something called albedo, and we have to talk about scattering. So albedo is basically that radiant energy being reflected away from a surface. How much light is reflected away from a surface? It's really how much energy, but we think about it as the visible spectrum because that which is light as we know it, because that's mostly what the sun emits. And it goes from 0 to, it's supposed to be, 0 to 100, yes. 0 means no light is reflected. That means all the energy that hits it is absorbed. And 100 means all the light is reflected away. So that means there would be no absorption, no temperature change. Can you think of a surface and we're thinking about this as far as the surface of the Earth, right? Can you think of a surface that might have a really high reflection rate of albedo? Okay, then we have scattering, which is more of like it takes the radiant energy and it scatters it in all different directions. It's not reflection. Reflection is in at one angle, out at another, where it won't change and it can be absorbed somewhere else. Scattering takes it and it breaks it up and it sends it all kinds of different directions. So we think about this with visible light, specifically like giving the sky color in sunsets. So let's look a little bit more at albedo. So the albedo of snow, here's a table that gives you some albedo values. The albedo of snow is extremely high. That might be one of the surfaces that you thought about that would be really reflective. It can be anywhere between 75 and 95%. And so part of the reason why the high latitudes, the Arctic and the Antarctic, are so cold is because whatever solar energy that it gets, 75 to 95% of it is not absorbed, it's reflected away. So remember, we're heating the atmosphere, we're absorbing the radiant energy at the surface, and then we heat that small layer through conduction and then convection, right? So if we're reflecting away 95% of the energy that we're getting, we're not going to get our atmosphere very warm in those places. That's why after this snowstorm, we're going to have some of our coldest temperatures because so much of that solar energy is going to be reflected away over the next couple days. Now let's look at the albedo of water right here. It's 10. That's low. Does that seem a little counterintuitive? Because normally you see light reflecting off of water. But if you look at a satellite picture from space of water, what color is it? It's kind of like a dark blue. Darker colors absorb more energy than lighter colors. So snow is white, it reflects a lot. Water actually is dark, even though like at the right angle, yes, you can have some reflection, but overall, water's albedo is low. So it's absorbing almost all of the energy. It's absorbing 90% of the energy that it gets. And that's no wonder why the equator is so warm. Look at a map, look at a globe, and see how much water is across the equator. It's almost all water. There's very little land. So there, we just have the water, the surface, absorbing and absorbing and absorbing all of that solar energy that's hitting it, even though it does have a high heat capacity. So it takes a long time to change that. So albedo of your surface really affects the heating you're going to get during the day, and like because of our differential heating, and how much energy your surface is absorbing. Lastly, for this part, we have scattering. The color of the atmosphere is determined by scattering sunlight. For instance, the sky is blue because the atmosphere scatters the shortest wavelengths. Those are green, blue, and violet. And it's more effective of scattering those than it is at the longer wavelengths. But as we get to sunrise and sunset, so this is like at noon. Okay, so the sun's right over us. There's very little atmosphere that the light is going through, and so there's very little light to scatter away. And the atmosphere isn't very efficient at scattering those longer wavelengths, even in the visible spectrum. But now at sunrise or sunset, the sun's light is going through a really long layer of the atmosphere. So there's more time, more atmosphere, more molecules to scatter away that light. And what happens is the blue light and the all the blue hues, the shorter wavelengths get totally scattered away, but those longer wavelengths start to scatter. And that's why sunrises and sunsets have those warmer colors that are longer visible wavelengths. Here, make sure there's anything else I want to see. Yeah, okay. So here we have a video. Please watch it. It explains much better in much more detail all about the scattering and why we see the different colors. That's it for this video, and we have one more before the chapter's over.